Okay, we're going to go back and talk about classes and types. Okay. So last week we talked about types. And one of the questions I gave you last week was define a type. What is a type? If I said to you, what is the definition of a type, or what is a type, what was the answer to that? A set of what?
Allowable values and operations.
Yeah, so it's a set of allowable values, and it was a set of operations that operate on those values. Okay? And so we talked about built-ins having true and false, and then some operations that can go on them. We talked about ints, a set of values as whole numbers, and then you can add and subtract. Okay, so on and so forth. Okay, so in C++, if we wanted to define our own types, we'd do it by defining a class. Okay? We can also define a struct. A struct and a class are essentially the same thing. Okay? The difference is to do with default visibility. Okay, so we are 99% of the time going to be defining classes. Okay? And so you should have all done object orientation before. Okay? So you should know things about public and private already, but if you don't, you have a class. So in this case, we've got a class book. General practice is to make your methods or your functions public, and the data that's encapsulated within the class private. It's not always true, but 99% of the time it is. Okay? So we have a class here. Okay? It's got a public method called ISBN. Okay? Or you could call it get ISBN. I would assume it returns an ISBN. Okay? And also there's an error on that slide. That declaration of ISBN should be telling me what it's returning. Okay? And then you have some private information. So in this case, the ISBN number is being stored as a string. There's an unsigned int of the number of units sold. And there's a double value, which is for revenue, obviously for the amount of money you make per book. Okay? So you have a class. A class is just a declaration and a definition, but a declaration is some code. Okay? Some code defines an object that's going to exist in memory. Okay? So you have a class, you then have an object. Okay? An object is a piece of memory with a type. An int can be an object. A string can be an object. Your book class that you defined and declared up here in code, in memory, becomes a book object. Okay? You can have many objects of the same type, okay? But generally you only have one type declaration. So you've only got one declaration and definition of book, being the class book, but you can have many book objects, okay? It's really important to get that cleared up between the two. A class is a declaration definition in code of something that's going to exist in memory, and the something in memory is an object, okay? And so there's two types of base objects, okay? There's a class object, like what you saw on the previous slide, okay? And a non-class object, okay? Non-class objects are typically your primitives, things like int. You can't say I.append, okay? Because I is just a primitive type, it's an int, okay? Whereabouts, if you're again coming from Java land, you actually, in Java land, you've got these two different things. You've got an int and you've got an integer, okay? You don't have that in C++, you don't have an integer, the same. But you could go build an integer class to do that, okay? And so again, up on the screen here, you have some variables. Variables are identified as being what's called named objects, okay? So the object in memory here is an int, its name is I, okay? So it's an int object with the name I. There's a string object, actually it should have standard in front of it, okay? But standard string S, okay? That's a string object called S with the value in memory of ABC. Next line, it also should have standard in front of it. Standard vector, okay? This is a vector object. It's a vector object that contains ints, okay? And that's a vector of 5 ints, okay? A vector is basically a dynamic array, or you can think of a vector in a similar manner to which you use an array list in Java, okay? Also be aware that C++ is case sensitive, okay? And a name must be declared before it's used, okay? So again, this stuff should mostly be revision. If you're confused, feel free to ask some questions. Okay? Okay, so we talked about a class. We've talked about an object. Let's talk about a variable. Okay? So a variable kind of brings all the stuff together. A variable provides a named storage area. It has a particular type. It is an L value. Remember we talked about L values and R values last week. Okay? So a variable is an L value. Okay? And it must be defined and or declared before it's used. Okay? And it cannot be used as an R value before it's initialized. Okay? What that means is I can declare my book class. I can create a variable of book. Okay? But I should not use it as in, say, bookb.isbn until I've actually created for book B in memory. Okay? This is more clear, again, if you're coming from Java, the difference between saying book B and book B equals new book. Okay? We'll talk about this memory and dynamic memory in Java and C++ later on. Okay? But there's the declaration and the definition. Okay? You can declare a variable. For point of declaration, it's an L value. And until you define it in memory, it becomes an R value, initialized in memory. Okay? So be very careful about that, because if you try to use a variable that hasn't been initialized, you'll get some sort of error. It will either be compile time or runtime, but you'll get some sort of error. Or if you don't get an error, further down your code, you'll get an error. Okay? So let's talk about initialization. Here are 6 different ways to initialize an int. Probably for line 4 is probably the only way you've seen before. Okay? But C++ 11 in particular introduced a whole new set of ways of initializing things. You can use what's called list initialization, which is line 1. Okay? You can also do list initialization with an equals, like on line 3. Line 4 is probably what you've seen before. We've actually just say int i3 is equal to 4. You can also say int i4 brackets 1. Okay? That kind of says that you're calling the int's constructor. Okay? Kind of. You can initialize it with a list that's empty. Okay? And that means the default value is used. Okay? Which for int, I believe, is 0. Okay? You can also do it on to line 8, similar way. Int j2 is equal to int open and close braces like that. Okay? And again, you have a temporary value at that point containing the default value that's then copied in. Okay? 6 different ways of doing initialization. Okay? This initialization, we're going to look at in detail probably next week or the week after, okay? Because when it comes to classes, this is quite important for how we initialize our classes, particularly again in C++ 11. Okay? And there's performance reasons why this is preferred. Okay? And again, if you've got the textbook, there's a whole section on this and about default initialization. Okay? In particular, some stuff to remember, and it's not on my slide. Okay, so definitely go read the textbook for this. With default initialization, depending on scope and depending on type, depends on whether things are default initialized or not. Okay? So, primitive types, like ints and floats and things like that, are generally always default initialized. Classes that you define yourself most commonly are not default initialized. Okay, and again, that can have performance impacts and introduce bugs into your code. Okay, so go read that section of the textbook. If you don't have a textbook, go pick it up. Okay? So let's talk about type checking. Okay? We say at C++ is strongly static typed. Okay? That means that the type checking happens when you compile the code. Okay? And generally, the compiler will produce errors if you're doing something that's illegal, not allowed. Okay? So that means a couple of things. What we showed you last week with unsigned int going to the int, that is allowed. That's why you didn't get a warning about it. Okay? It wasn't a type error. If you try to convert an int to a complex number, That hopefully will give you an error because that doesn't make much sense, okay? But an unsigned int to an int, even if it's a little bit weird and we probably shouldn't be doing it, it's allowed because it's not a legal operation, okay? So types must be known at compile time, okay? So it means that we can do things, well, we can't do things like this. We have floatf. We have a pointer to a float. That's fine, okay? Because there's a relationship going on between the float pointer and the float, okay? The float pointer and the float are not the same type. Okay, let's be very clear about that. The float pointer and the float are not the same type, okay? But they have a relationship. The compiler knows how to handle them. On line 3, when you say int pointer, okay, that doesn't make sense, okay? The int pointer does not make sense. You cannot have an int pointer to a float. You can convert an int to a float, okay, but you cannot have an int pointer to a float. That doesn't make sense, and the compiler will error. Actually, also, it's another error on that slide. We've got 2 declarations of P, okay? So it's two errors on that slide. One is for int pointer, and the second one is, even though for int pointer and the float pointer are different types, you use the same name twice, okay? So you can't just go off a different type, therefore it's a different name. That won't say, therefore the same name, that won't work. The name needs to be different. Okay. So when talking about type conversions, again, there's a couple of things that we can do. There's implicit, which means the compiler just works it out. And then there's explicit, which means that we program additional rules into our programs about how to convert our types. Okay? And so we talk about the idea of promotion. And promotion is value-preserving conversions. That means converting things like a bool to an int. Okay, so the booleans are only true or false, 1 or 0. We can convert that to an int because the int can hold those values. We can convert an int to a long. Remember, a long is just the same as an int, it's just got more memory, so it can hold larger values. And that's fine. It's promoted to these particular types, and the value that's stored in it is preserved. It's not lost. It's not condensed. It's the same value. It keeps on working. Okay. However, as you can see on the bottom of that slide, okay, this is similar to our signed and unsigned problem. Okay. We can say int pi is equal to 3.14, and pi only gets a value 3, and there's no compiler warning. Okay. So, again, you should be aware of all these things already, but be very careful when you're converting between types. Okay. So what you've done up until this point, hopefully in C, is you've done what's called static casting. Okay. That means that when you do get an error, you go and tell the compiler exactly what you want to do in terms of that cast. So we can do static casting in 3 different ways. We can say double my double, 3.14. Okay, so we've got a variable, 3.14, it's a double. We can cast it to an int by putting brackets int in front of my double, like on line 2 up there. We can cast it to an int, and you might not have seen this way around, but in a similar way to how we'd use a constructor. We can say int, brackets, give it my double, and it casts. We can also do a C++11 style cast, which is very explicit, okay, so it's a lot of code to write, but it's very clear what you're trying to do. That line 4, where it says int cast3 equals static underscore cast int my double. The reason why it's recommended is for an int, that probably makes sense. If that wasn't an int in here, say you're trying to convert this to a complex number, okay, or some other type, okay, this is very explicit in what you're trying to do. Okay? And so probably a very well-known example is integer division. Okay? Say we have int I equals 5 and int j equals 2. If we say I being 5 divided by 5, okay, 5 divided by 5 is 1, that's fine. If we say, set for argument's sake, 2 divided by 5, Okay, 2 divided by 5 is 0 for the sake of int division. Okay? And what you would have done previously is you would have converted one of these, or cast one of these to a double, like up top of there. This is the preferred way of doing it, static cast double, like that. Okay? Again, just stick this all in the back of your mind. Some of this will be revised in assignment 2. Okay? So come back to some of these slides when we get to assignment 2. Okay? So that's the first type of cast. This is probably all the casting you've seen before. Okay? There's another type of cast. It's called a reinterpret cast. Okay? As you can probably guess, a reinterpret cast is reinterpreting the low-level bit pattern. Okay? Reinterpreting what's happening down on the bit level of your code. Okay? So we've got a program here. I'm not sure if I've got this one as a... Oh, I do. Recast. Okay, so I've got recast.cpp. Okay? So you can go check this out in your own time later on. Okay? But what this is doing is it's creating an array of 20 ints. Okay? For each of these array of 20 ints, it's calling this function hash up here. Okay? Which returns a short. Okay? So the short is getting returned out of there. It's getting printed out. Okay? And then it's getting the value of A plusing I. Okay? Is anyone confused about what this is doing at this point? Okay, this is taking a void pointer as well. Okay? So this code will take you a while to understand what's going on. Okay? Array of 20 ints then. Okay, that array of 20 ints are all going to be default initialized to 0. Okay, but you've got an array of 20 ints in memory. That's hash A plus 1. That's getting the memory address to go into that pointer up there. Okay, because we're doing a C-style array. Okay, so that's a pointer. Okay. What we are saying is reinterpret our pointer, which at the moment is actually void. So reinterpret at the bit level this P to a long. Okay. And then go and do some bit shifting on it. Okay. So it's doing a whole ton of bit manipulation to turn this pointer address, which is a long, a very big number, compress it and calculate some sort of hash of it and return it as a short. Okay, so we are reinterpreting the bit level pattern of what's going on. Okay? And so we can do this, we can make recast. Okay. And so what's going on here? Actually, we should print out these numbers. So what I'll do, so I'll change this program ever so slightly to print out the address of A. Okay, so now you'll be able to see the address, and you'll be able to see the hash value. Okay, so you can see those memory addresses changing, those hash values changing. Okay. Also note, each time I run this, the values change. Okay, that should be obvious to you. Why are the values changing every time I run this? Who knows? Why are these values changing every time I run this program?
Putting the array in a different place.
Yeah, putting the array into a different place in memory. Okay? Again, hopefully no one would ever do this, but be very careful when you work with memory. Don't store those memory addresses out to disk and then try to read back into the same piece of memory next time through. Don't do that. Okay? So every time I run this program, the values change. Okay? Because the location that the program is running in memory is changing. Okay? And that's operating system dependent as well. It's possible I'll run this twice and I'll get the same piece of memory twice, but it's very unlikely. Okay? So reinterpret cast. Okay, got your idea of how you're doing that? You don't need to necessarily understand all the bit shifting that's going on there, but what's happening with a reinterpret cast is looking at the low-level bit pattern of what's going on and changing it. That's different to our static cast. Our static cast is looking at just the value, the interpreted value at that point. Okay? So static cast, looking at the value. Reinterpret cast, looking at the bit pattern and shifting things on the bit pattern level. Const cast. Const cast casts away the const. So we talked about const last week, and we said that you put const in front of something to make it constant. Well, C++ lets us do dumb things. And the dumb thing it lets us do is lets us make something constant, and then we decide it doesn't want to be constant anymore, so we can cast away that const. And we can go modify it. Okay? So the reason why is the slide in red says avoid doing this. Okay? You very rarely use this, but you use it for argument's sake if you're working with some old code. Okay? And the old code might be set up not to have something constant, or might be set up to have something constant, and it's not quite working right. You can cast away that const and allow you to go modify things underneath it. Okay? Very powerful, but also very dangerous. Okay? So generally try to avoid doing that, okay? But that's another type of const that you can do there. Okay? If you go read the textbook, I've deliberately skipped over one of the casts here because it's quite different again, and we don't need it for this course. Okay? But there's a fourth type of const. Sorry, not const. There's a fourth type of cast that works a bit like a reinterpret or an instance of. Okay? It happens at runtime. But go read the textbook for that one. Okay, we're clear on these different types of casts at this point. Okay, 99% of the time you'll be doing a static cast. Okay, just store away, reinterpret cast and const cast into the back of your mind and come back to that if you need to.